I don't know if anybody else streams it while you're in here, but if, let me know if it's working or not. Both of mine. All right, so now there are two streams active, it looks like. It looks like we're on chat, so one of them's working. All right. All right, then we'll go ahead. I don't have it, so but we do have the chat up, and we of course have Piazza. So to continue from where we left off last time, hopefully it's working. Remember that we started looking at searching and sorting in practice, with the idea being that you don't roll your own. You don't make your own linear search algorithm. You don't make your own binary search algorithm or your own sorting algorithm. Instead, what you do is you use what's built into the language or built into a standard library in the language that you're using. To do that, you need another component here, because if you're going to have one sorting algorithm, that sorting algorithm needs to be applicable to when you're sorting integers, when you're sorting doubles, when you're sorting films, or when you're sorting students, or when you're sorting airports, like you're doing this week. So to keep that generic, you need this other component over here, because the sorting algorithm knows that, well, if these two things are out of order, I need to swap them. Or if it's quicksort, you've got a pivot element. This thing is less, so it needs to go over here. This thing is greater, so it needs to go over here. It doesn't need to know anything about those things, that A and that B, though. Instead, what you do is you provide it another component called a comparator that does know everything about A and B. And that it knows that A comes before B, and so it returns something negative. It knows that A is equal to B, so it returns 0. Or it knows that they're out of order, that B comes before A, and therefore it needs to return something positive. Okay? We looked at that very briefly with comparators in C, noting that they have the following signature here. In fact, we even went over an example with integers. We'll review that today here. It returns an integer, like the contract over here. It returns something negative, positive, or 0, depending on the relative ordering of those things. Both of the arguments are generic void pointers, because again, you want to keep this generic. You can't just pass in integers all the time. You can't pass in doubles all the time. It needs to be applicable to any type. It's const because it's not going to be making any changes to it. And you follow the same basic structure, that you force them inside the comparator. You force A and B to become a specific type, integers. Now you know something about them rather than just that they're raw memory addresses, and you know how to order them. Right? We went through an exercise of creating a comparator function in C. We also briefly looked at what it might look like in Java. What I want to do is I want to take a little bit of a detour and understand this a little bit more before we get more practice actually doing them. So to do that, I've brought over here a demonstration. The way that this works is through what's called function pointers, right? So what are function pointers? Well, what's stored in memory? In a computer, everything is stored in memory, right? So for example, what? Data, right? If I have an integer, I store 42, and I store that in memory, then that's where I store it. What else is stored in a computer? Module 10, what did you cover? Files, right? Files are stored in memory. What else is stored in memory? Programs, right? So it makes sense that I can have a pointer to data, right? In fact, that's what I've done over here. I've got an integer, I can make a pointer to that integer. It makes sense that you have pointers to files. In fact, that's how C works, right? File star F, when you do file IO, whether it's input or output, that is a pointer. Well, then it also makes sense to have pointers to programs, because those are also stored in memory, right? And consequently, you can create a pointer that points to a specific function in your program, or outside of your program as well, right? Now, I'm going to show you how to do this, and then we're going to discuss why, during this, why you would want to do something like this. So let me go ahead and create a pointer to a function. So let's go ahead and create a pointer to a function. that returns an integer and takes 3 arguments, say a double, an int, and a char. So to do that, I'm going to look at this for inspiration. So it returns an integer, so I'm going to type int, right? And then it's a pointer, so it's going to be int star, and I'll say ptr2func, short for ptr2 function. I'm making a pointer that's going to point to a function. Now, if I just end it right there, is that a function pointer? It doesn't look like it. It looks like what? It looks exactly the same as up here. It's just an integer pointer. So what I'm going to do is I'm going to add more syntax onto this. First of all, you remember when we looked at structures, there's a difference between using the dot operator and the arrow operator. And that's because you have a pointer to a structure, you use the arrow operator. And you have a regular old structure, you use the dot operator, right? An alternative to the arrow operator would be to dereference it, but what did we have to do? We had to surround that with a couple of parentheses because of the order of operations. And I have to do the same thing here. That's not an integer pointer. That is a pointer to a function now. What kind of function? A function that returns an integer and takes a double, an int, and a char. There's a function pointer. That is a pointer that can point to any function that takes 3 arguments, one being a double, integer, and char, and returns an integer. How do I make it point to a function, such a function? Well, first of all, I need a function. So int foo double x int y char c, right? And then I'll just return 0 here. I don't care what the function actually does. It's just foo, right? Well, how did I make a ptr to x point to x? ptr to func, how do I make it point to foo? Following this pattern right here. Ampersand foo. Why ampersand? Because it gives you the memory address of that thing. Now it turns out that you don't actually need to do this, or better, shorter, equivalent. In C, a function's name is its reference. We've seen that before, right? If I have an integer array, int star arr, what is arr? It's its memory address that you can pass to a function, right? Same thing here. Foo is its memory address, and I'm making it point to foo. Give me another function that you're aware of. Say from the math library, it doesn't matter. Sine, okay. Could I make ptr to func point to sine? Maybe. Let's find out what happens here. GCC function pointers, right? And then of course LM for the math library, and it's complaining. It's going to allow me to do it. It's not an error, but it's certainly a warning. Why? What does sine take? How many arguments does sine take? One. A double. What is this pointer saying? I'm a pointer that can point to a function that takes 3 arguments, a double and a char. Can I make one point to the other? Probably not. Not without consequences. That's what it's warning me about. Just like you can't make an integer pointer point to a double, right? If I made this integer pointer here, ptr to x is equal to y, where y is a double, right? If I did something like that, you can't make you can make an integer pointer point to a double, but you're not going to get expected results, right? So don't do this, right? This is invalid, right? Warning. Right? All right, so let's go ahead and make a pointer that can point to sine. Sine returns what? A double. And I'll have ptr to sine here, pointer to sine, and double, and it takes a double. Now it is perfectly valid to go ahead and make this point to sine. And you can even use it. In fact, I'm going to go ahead and get rid of this so I don't get my warnings anymore. All right. I'll leave it in there though. And no warnings here because you are making the proper pointer point to a proper function here. Now, why would you want to do this? Well, you could do things like this. Double y is equal to sine of 2.0. Right? This is calling a regular function through its regular name, right? And printf y is equal to %f and the line y. So if I were to compile this and execute this, excuse me, there we go. Then I get the expected result, 0.9 something, right? Now remember this is in radians. So if you want to, what is sine of approximately 3.14159? What should I expect now? 1 radian, sine is 1 radian of what? Negative. 0, right? I never remembered either. That's why I was asking you, right? All right, so apparently it's going to be 0, right? Sine of pi is 0. It's not exactly 0 here because I'm not exactly giving it pi, right? Well, I can do the same thing, but through its pointer. PTR to sine, and I'll pass in 3.14159. Right? There we go. GCC, and run it, and I get the same result. What's the point? You've already got sine. Why don't you just call it like you do up here? Why do you want a pointer to be able to call a function? Yeah.
Can I just ask a question?
Sure.
So how can we give a pointer an argument?
That's a good question. So how did we do it?
Like then we assign it to the...
Oh, wait. So are you invoking the function or not?
We are.
Okay, you're invoking the function right here on line 32. How do I give it the argument? Parentheses, and then this.
Is that only when you assign that pointer to a function?
That's the only way that you can do it, yeah. Right. I mean, you could do something like this. PTR to x of, I think you could do something like this. It's weird. The compiler will or will not care about this. No, it's not a function. It's going to realize it's not a function. But it realizes that this is a function pointer, and therefore you can invoke it. So it would be a syntax error if you tried to do something like that. Does that answer it? Okay. But by your act of putting parentheses there, and then anything that you put inside there, says to the compiler, I am invoking this function, I'm calling this function. Right? If I just print it out, for example, I could say that printf, the function sine is stored at memory location %p for a pointer, right? And then print out ptr to sine, right? And run it. Well, I'm just going to get some stupid memory location that changes every single time I run it because, of course, the program is loaded up in a different memory location each time, right? Okay. So why would you want to do something like this? It's so that I can hand this function off to another function so it can call it. I don't want to call it. I want to tell that function to call that function over there. And to be able to do that, I need to be able to have a way to tell that function which function to call. Think about it like this. And we'll get into graphical user interface programming a little bit after the break. But think about this button here, right? This button that says save. How do I specify how it saves? Well, one way that I could do that is I could say that when this gets clicked, open the file, write to the file, save the file. Write 3 pieces of code there in whatever function encapsulates this save button. Right? A different way, a better way, would be to say keep it generic. When I create this button, I say, oh, button, when you get clicked, go ahead and call that function over there. When you get double clicked, call that function over there. When you get, it's not a thing, but when you get triple clicked, go ahead and call that function over there. What am I doing in each one of those cases? I am pointing to a different function. Call that function over there because I'm not actually clicking the button. I'm saying in the event that you get clicked, call that function over there. Right? And to be able to do that, I need to be able to pass this function off to another function. What might that look like? So double run math. Right? What I'm going to do is I'm going to give you an input here, double x. That's our input, I'll call it. And then I'm also going to give you a function, right? A function that returns a double, and I'll call it f, right? And returns a double, and takes a double as input. Right? Now, I can go ahead and return f on input. There we go. Oh, fun math. Maybe it is fun. I'll go ahead and I'll leave it like that. I meant to write run math, but fun math, sure. All right. Make it a little bit fun. So why would I want to do something like this? Now I can go ahead and say fun math on 3.14159, and I can pass in sine, just as before, and get the same result. Or I can go ahead and say run cosine instead. Cosine of pi is what? That's -1? Okay, all right. Or I could say, go ahead and run tangent on that input. What is tangent of pi? Anybody? Is it 0? All right, so -1 and 0, yes. It's -0, but it's not exactly because the pi I'm giving it is not exact. Right? I can hand this function off over and over and over again and give you completely different results. Now, I could also do a square root. Right? What's the square root of pi? Apparently 1.77, something close. Right? Why? Because I'm giving this function off. This is called a callback. So when you get the save button, when you get clicked, call that function back over there. Right? Call it back. Right? A callback in regular old life is a reference to something that you've heard before. Right? I've heard of that function before. Go ahead and call it back. Right? That's my best explanation. Right? It's a callback. Right? And you do this in graphical user interface programming. You do it in, say, searching and sorting algorithms, where you've got this generic algorithm that it knows how to sort. It knows that if these two things are out of order, it should swap them, and it knows how to do that for everything. It just doesn't know how to determine whether or not these two things are out of order. To do that, I need to give you a function that looks like this in order to compare those two elements, keeping it generic. All right? So questions on function pointers? You won't have cause to write your own generic functions, at least in this version of this course. So I don't want to get into it too much deeper, but I will go ahead and make sure that you've got this in the notes. Right? What I want to do is I want to focus on actually using this stuff now. So we've got our array here of numbers. There are 9 of them. I print them out, and we see that they're not in any particular order. What I want to do now is I want to use the standard library to do all my searching and sorting for me. I don't want to have to write my own algorithms. In fact, I've taken them out. All these algorithms that we wrote, throw them out the window. All right? We don't need them. All right, so the first thing I need is a comparator for integers. So I'll document this. This comparator orders integers. It orders them. It does not sort them. Right? Given 2 integers, it says that they go like this, negative. They go like this, positive, or they're equal, 0. Right? Integers in ascending order. I'll just go ahead and go with ascending, and we'll take care of descending later. Right? So I should return an integer because that's what a comparator does. Return something negative, positive, or 0. What should I call this comparator? Should I just call it CMP? All right, probably call it CMP int. And you could go ahead and add ascending here, but usually in programming, the natural ordering is always in ascending order. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, that's going to be the default anyway. Right? Yeah?
So it's like, if it's the order descending for some reason, just put...
I would probably want to label that because that's not standard. That's not the default, usually. Right? If you want to be explicit about it and go ahead and go with ascending, great, go ahead. But I'll just go ahead and put that into the documentation here in descending order. Right? So, does it take 2 integers, int A, int B? Is that a comparator? Doesn't look like it to me. Right? It takes integer pointers. Yeah, that doesn't look right to me either. It takes what? Void pointers. It still doesn't look right. Const, right? Because we're going to be making a promise here. I'm just saying, oh, A, B, all right, well, they go like this, they go like this, they go like this. Right? I'm not actually changing them. I'm not actually moving them around either. That's what the sorting algorithm is going to do for me. It just says that they go, A comes first, B comes first, or they're equal. All right, first step. 1, cast the pointers into the expected type. And for us, that's going to be const int star x, and cast A as const int star A. Right. We've seen this before, haven't we? This kind of pattern, where I've got a void pointer that I'm going to force to become an integer pointer, so that I can do things with it. What returns a void pointer that you've seen before? Not yet. Not qsort yet. Malloc. Malloc returns what? A void pointer. Why? Because you don't want a malloc for integers, a malloc for doubles, a malloc for films, a malloc for students. You have one malloc that simply gives you a chunk of memory. Whatever you do with that memory is your business. This is just a chunk of memory. Whatever we do with that memory is our business. I'm going to force it to become an integer in this case. Now, if I passed in two doubles, right, would that assumption be valid anymore? No. Just like our function pointer example here, if I forced an integer pointer to point to a double, I'm going to have a bad time. Right? All right, so come back over here. I forced them to become integers, and now I can make some comparisons. You may want it to, you may even see it out in the wild. Somebody immediately using what's called the difference trick. Right? Did we talk about the difference trick? So if y is 10, x is 5, then this will be, the difference here will be 10 minus 5, positive. They're out of order, right? 5 comes before 10. If we've got 5 minus 10, that'll be negative, right? And so they are in order. If we've got 5 minus 5, will be 0, and so they're equal. So it looks correct, doesn't it? But it's not. What if I had 2 billion, 1, 2, 3, 1, 2, 3, 1, 2, 3, minus a negative 2 billion, 1, 2, 3, 1, 2, 3, 1, 2, 3. What's the value of that? Is it 0? 4, mathematically it should be 4 billion. Can you hold 4 billion in an integer? Nope. Underflow giving you a negative value, meaning that it's giving you the wrong ordering. Right? Don't do that. Tricks are for kids. Right? Don't do tricks like that. Right? Instead, be explicit. If x is less than y, then I will return something negative. Now, before I go on, is that how I compare two integers? I need to what? Dereference it. Why? Because they are pointers. Change those pointers into regular old variables so that you can use this less than. Right? Else if x, dereference x is greater than y, then what should I return? I could return something positive, 42, right? Or mash my keyboard, something like that. Too big, right? Something like that. Why be weird about it? Right? Negative 1, 1, 0. Right? Else return 0. Right? Make no assumptions on the magnitude of the value that it returns, because somebody could go in and be weird about it. Right? Don't assume that it's negative 1. Don't assume that it's positive 1. Don't assume anything about that it's negative 42. Just assume that it's negative, positive, or 0. Right? That's the only thing that you can assume, because that's the contract. Okay? Now, how do we go about using this? Well, there's this nice little function called qsort. What do you think the Q stands for? Quick, right? We talked about quicksort. At least I gave you the high-level idea that you've got this pivot element. Things that are less go over here. Things that are greater go over here. And then you recurse on those two subarrays. Right? Qsort is actually not necessarily a quicksort implementation, but it was named that 40, 50 years ago. And so consequently, we are stuck with the name. You can, where's the actual signature? I'm looking for it. Here we go. All right, here we go. So here are notes. C provides its standard quicksort implementation. That's why I'm saying it's quicksort. It may or may not be quicksort. It could be merge sort. It could be timsort. It could be a non-recursive implementation of quicksort, et cetera, right? You'd have to read the documentation, actually probably even open up the source code to find out what it's actually doing, right? It's probably doing some sort of hybrid sorting algorithm, which is more efficient in practice. It takes 4 arguments. That first one is what? Void star base is the array you are sorting. There we go. Void star. Why is it a void star? Well, first of all, it's an array, so it has to be a pointer. Why void? because you have one sorting algorithm to rule them all, right? It's not an array of integers, it's not an array of doubles, it's an array of stuff, right, of things. Nel, the second one, anytime that you pass an array to a function, what else do you need to pass it to an array of, or to that function? Number of elements, right? That's what nel stands for, number of elements, right? What about size? Size is the number of bytes each element takes. Right? Why would it need to know that? Quicksort is going to look at the things stored in your array, right? And it's going to look and say, all right, here, I'll pass these off to the comparator. The comparator says these are out of order. I need to swap them. So what does Quicksort need to be able to know? How many bytes this is and how many bytes this is. Because if it's an integer, it could be 4 bytes, copy it over here, take these 4 bytes, put them over here, put these 4 bytes over here. If it's a double, take these 8 bytes and swap them with these 8 bytes. If it's a student and it's 40 bytes, take these 40 bytes and swap it with these 40 bytes over here. Yeah?
So the quicksort function can tell by looking at your array what type it is. Like if it's
Nope, it could be anything because it's void. It's just memory, whatever, right? And it doesn't want to know. That's why you have to give it the comparator. And that's the last thing. This weird syntax is what we just learned, right? This compare with a star in front of it, but parentheses around it, that is a function pointer. I'm going to hand off the comparator to say, use that comparator to ask about whether or not these two things should be swapped because they're out of order, or they're in order, leave them alone, or they're equal, break ties however you're going to break ties. Right? So what does that look like when we actually use it? Right? So come back over here and qsort. I need to pass it those 4 things. The first thing is going to be the thing that I want to sort, numbers here. The second thing is the number of elements, and I've already stored that into a variable n. There are 9 integers in that array, if you count them up. Right? The third thing is the number of bytes that each element in numbers takes. Each element is an integer, so how many bytes does an integer take? 4? Mostly, yeah, but is that the way you should do it? Size of int, right? Now that's interoperable. And then the last thing is the function that you want to use to make comparisons. And to do that, I just need to pass in the function name. It is not correct to do this because I would be calling that function, and then it's even less correct because I'm not even giving it any inputs. Right? You want to pass the name of the function as its pointer. You could do ampersand, but why? Right? Just go ahead and give it the name. Now let's go ahead and print it again to verify that this is actually working. So let's go ahead and print this nicely. Printf, end the line, and then I'll end the line down here as well. So the first time, it's exactly as I gave it, 42 through 0. The second time, however, it is sorted in ascending order, the default. Cool? Let's resort it in descending order now. So, copy, pasta, rename, descending. Make sure that your documentation is up to date, descending order. What's the only difference between those two? Instead of greater than, I would, less than, I would do greater than. Instead of greater than, I would do less than. And if it's 0, then return the same thing. Right? That seems like a lot of repeated code for just a little bit of a change. Better ways? All right, have one function call the other. How will that work? Oh, okay. Here's my first attempt. -1 times CMP of int. You immediately jump to the best solution. Right? All I'm doing here is negatives become positives, positives become negatives, zeros stay the same. Right? Or, without the multiplication, just negate it. Or, without even that, just swap the arguments. Right? And now I can call quicksort using that comparator instead, CMP descending. And it's in reverse order now. 101 down to 0. Okay?
Is there such a thing as a generic comparator?
Man, you just no way. You know, I guess you could do it byte for byte, and then use a built-in less than or equal to. But then, I don't think that conceptually it wouldn't make any sense. You're just sorting characters at that point, and then so if I put in hello, it would just simply rearrange that word into EHLLO. Yeah.
So when we're passing the function, we're passing it as a pointer?
Yep.
So
Because the name of the function is its pointer, just like the name of an array is its pointer.
so if we put an ampersand, does it matter? Or is it
Nope, it doesn't matter in this case. It would matter over here
Yeah.
because that's giving you the memory address of the pointer. So it's giving you a pointer to an integer, and that's not what you want. Right? But this and this are basically the same. Right? Okay. I don't know if that's syntactic sugar or if there's something deeper going on there, and there actually is a difference, but why write the ampersand if you don't need to? Okay. What if I created another comparator for doubles? Let's do this. CMP double. Right? Now this is perfect. What are the differences? What's going to be the difference here? Orders doubles in ascending order. Well, I don't typecast them as integers anymore, do I? I change them all to double, 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 and double. Now, technically, a lot of repeated code here as well, but I'm forced to because one's 4 bytes, one's 8 bytes. You can't do it. I mean, you could. No, you wouldn't want to do it. You wouldn't want to take a shortcut here, right? In fact, you certainly don't want to do the difference trick now. What if I did y minus x? Let's take some numbers here. 3.75 minus 3.25 is equal to positive 0.50. What happens to that 0.5 when you return it? Integer truncation, and so it becomes 0. 3.75 is equal to 3.25? Nope. Lots of reasons you don't want to do the difference trick. Don't get fancy, right? Just have an if, else, if condition here, okay? What if I had used that, though, in quicksort? So I've got an array of integers, but I give you a comparator for doubles. Would you expect that to work? Let's find out. Yeah, you're complaining. Oops, not descending. What is it? Just doubles. There we go. I wonder what's going to happen. All right, well, it worked. 0 at the end, right? Did it actually sort? No, right? It did something weird, right? Unexpected, undefined behavior. Because I gave you an array of integers, but a comparator for doubles. That's not going to work, all right? All right, so we now know how to properly sort in C. What about searching? Searching in C. There's another one called bsearch. Where are you? All right, I don't have the... All right, fine. We'll look up the man pages on bsearch. What do you think the B stands for in this case? Binary search. There's also a linear search. There's lfind and lsearch. Go ahead and look those up yourself because they do have different behavior. But you'll see here that this is in the standard library. The qsort is in the standard library. Let's go ahead and talk about them now. So see. Oops. All right, so I'm going to go ahead and reformat this. There we go. You go to the next line, and you scooch over. There we go. Look at those two signatures and tell me what the differences are. First of all, qsort, does it return anything? No, why? Here's your array, right? It changes it and it says, okay, I'm done. I sorted your array for you. There's nothing to return, right? There's no error handling here. B-search, on the other hand, returns something. What does it return? Returns a pointer to a matching element if found, right? So if it's an array of integers, it will return an integer array to the one that it found that matches your key, right? What do you think if it didn't find anything? If no such element is found, returns what? Null. Right. Okay, that's the first difference. What's the second difference? The first one takes 4 arguments. These are the exact same 4 arguments, right? This is the array that you were searching. This is the number of members, elements in that array. This is the size, the number of bytes of each element in that array. And this is the comparator that you use to search. But the key difference here is, are you going to be making changes to that array? Here we were. Here we are not, right? So B-search does not make changes to the array, right? It is const. Right? The last difference is that it takes a 5th argument, the first argument here. Finally, the first argument is a key that you are searching for. Right? So if you want to search for 42, you would create a key containing 42, create a pointer to it, and then hand that off to B-search because it expects a void pointer. Let's see how that works. Yeah, go ahead.
It looks like we return a void for B-search.
Oh, say what?
Are we returning void for B-search?
Nope, we're returning a void pointer.
Okay.
Right? Yep. Up here, just void. It doesn't return anything. Here, it returns a void pointer. Arguably, you go back 40, 50 years and tell Kernighan and Ritchie, come on, use some different names here to disambiguate what you're doing. But then you'd probably, if you had that luxury, you'd probably go back in time and tell them, don't use pointers. Because no other language really does. I mean, we have the concept of pass by reference, copy by reference versus pass by value, copy by value, but it's not as low level and explicit like it is in C and C++. Right. So let's go ahead and search for 42. Right. First of all, I need a key holding the value that I want to search for. Okay. And then I need to make sure that let's go ahead and create a integer star result. Right? And I'm going to go ahead and call B-search. Right? What are the arguments that I pass to B-search? First of all, it's going to be the key. Does it look like this? Key? Tell me about key. What is it? It's a regular old integer, right? That's not what it's expecting. It's expecting a pointer. So how do I take a regular old variable and make it into a pointer? Ampersand. Otherwise, the rest of it's the same. Numbers, the number of elements in there, n, size of int, because that's how many bytes each one takes, and finally the comparator that you want to use, Strcmp int, say. Now remember that this is wrong, and I'm going to show you that it's wrong here in a second. Right? Remember that, let's see, that it returns null. So if it's unsuccessful, null, printf, no such element %d exists, and the line, and a key. So if it returns null, then we know that it was an unsuccessful search. Else, printf, element found at memory address %p for a pointer containing value %d, we're going to dereference that. So result, and how do we dereference result? With a star. Yeah, go ahead.
Why do you need a comparator if you are correcting?
I need to know when I found the needle in the haystack. I need to know when the comparator says that's equal. The key and B are equal. You found what you're looking for, right? Or in the case of B search, if it's already sorted, right? You jump to the middle and you need to know, okay, well, the key that I'm looking for is greater, so I go that way. Or the key that I'm searching for is lesser, so I go that way. It needs to be still be able to say that this is the thing that you found, that you're looking for. Right? Now, I would argue, I would agree with you that why is this necessary? Because you're not actually moving things anymore. I'm going to look into that. I don't know. I don't think it is necessary. In fact, if you rip open the code, I don't think it's probably used anywhere. That's my suspicion. Right? Yeah.
So is it just so that everything's standard, you always pass it?
That would be my guess. That it follows the same exact signature, so that you don't get confused or something, right? Because I mean, if you don't look at the documentation, which one comes first, the number of elements or the size, or is it the size and the number of elements, right? I don't know, right? All right, let's run this and see if it actually works. First of all. So we're searching for 42. Element found at memory address blah containing the value 42. Great. That only worked because we got lucky here. Right? What if I had used a different comparator? What if I had used instead, say, this up here? I ordered it in descending order, but then I searched it in ascending order. 42 is in there. It should result in a successful search, but it doesn't. Why? Because again, it is sorted in descending order like this. So binary search looks at the middle 12 and says, oh, 42 is greater. It must be on this side of the array. But it's not, right? Because it's sorted differently. So don't do that, right? For binary search to work, it needs to be sorted with the same comparator. So let's get it to work here. Use the same comparator. It doesn't matter which, right? Still finds it at 42. If you use descending to sort it and descending to search it, you'll still get the same result. Still contains 42. Right? You just have to be consistent about it. Right? And certainly if you are inconsistent and use something completely different, say double, maybe seg fault here, but I doubt it. Oh, no such element 42 exists. Right? You can't even find it anymore. Right? That's why it needs the size. There we go. Because it needs to know, where do I go next? What is the middle index? In order to know the index, it needs to know the offset from the original memory location. And so if you need to go to the 5th element at index 4, it needs to go how many bytes over, size of int bytes times 4, and then it jumps to that memory location. And that's why it's necessary. Right?
So, what if you don't know the exact value? You just want the highest number or the lowest number?
Oh, good question. So if I sort it in descending order, where is the highest number?
The first one.
First element. If I sort it in, where's the lowest number if I sorted it in descending order? Last element. Right? Where's the median? Middle element. Right? Yeah, something like that. It depends on how you define median. Right? Because if it's 5 elements, then sorted, it's this guy. But if it's 4 elements, is it this guy or the average of these two guys? Then depends on how you define it. Right. All right, questions on this so far? Okay. Let's talk about it in Java. Right. So here I've got the exact same list of numbers. Last time I gave a preview of what this might look like. We do not have we don't have pointers in Java, so therefore we don't have function pointers. Instead, if you want to create this comparator, you need to actually create a class called, and what I'm about to do here is what's called an anonymous inline class, comparator. Did I spell it right? And I'm going to specify that this is a comparator for integers. And I'll just call it CMP int like I did before. Right? Now, we haven't defined this yet, but if you wanted a comparator for doubles, what would it look like? Double. If you wanted a comparator for student, you'd parameterize it with student, right? Dot, 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 right? So integer. By the way, you cannot create comparators for primitive types, right? You can only do it for the wrapper types. Integer, big D double, right? You can't do it for the lowercase ones, right? It's just you can't do it, right? It's not built into the language. I'm going to go ahead and create this new comparator for integers. I don't need to repeat the parameterization. You can if you want, but I'm not going to. And then I open bracket, closing curly bracket, and everything in here is what's defined in the class. This is actually an interface. We're not going to get into it too much here, but the, comparator, there we go. I spelled it right? There we go. Yeah, I did. Now it's complaining that I need to add the unimplemented methods. The only method that this class, that this interface defines is compare, right? It's public. Anybody can access it. It returns an integer. Exact same contract as over here. You will find this in every programming language, this exact same contract. You've got this comparator that returns something negative, positive, or 0, depending on the relative ordering of these things. Every language has something like this because they all don't want you to roll your own sorting algorithms. They just want you to define a comparator object or function or something or lambda or something, whatever the language supports it as, and then it'll take care of the sorting for you, right? This compare takes 2 integers. I like, this is just auto-generated code. I like to go ahead and rename them as A and B, right? And it returns an integer based on the relative ordering of these things. So if A is less than B, I'll return -1. Else if A is greater than B, I'll return +1. Else return 0. Right? That's one possibility. Another possibility is that there's a built-in comparison, right? Over here in C, how do we compare strings? Strcmp, right? That's already built into the language. Over here in Java, everything is built into the language for the primitive types, or for the built-in types. A.compare to B, right? You remember we did this with strings? String A compare to string B, and apple comes before banana, unless, of course, it is capital B, and then capital B banana comes before lowercase a banana, apple, because of lexicographic ordering. Here, these are integers, and the same compare to function is built into it. All I need to do is return it. Okay. Yeah, go ahead.
So why can't this just be like a public method outside of your main class?
Everything in Java is a class or belongs to a class. So I could put it as a method like, say, right here, right? I could say public int cmp int integer a integer b, right? And blah, blah, blah. Well, okay. Return I won't write it here, but now this belongs to the demo class, meaning I'd have to create an instance of the demo class. Demo has nothing to do with comparisons, right? So, okay, fine. I'll make it into part of the class, static. Now it has even less to do with comparisons because now it belongs to the actual class instead of instances of the class, right? This is an established interface. A comparator always has this function right here, right? And now what I can do is I can pass that off to a sorting algorithm. In this case, it's not qsort, it is collections.sort. And you pass in the thing that you want to sort, in this case numbers, and the comparator that you want to use for sorting, cmp int. Let me go ahead and print it. System.out.println before numbers, there we go, and after, and we'll see how it's been sorted. There we go. All we have to do is create a comparator, simplify it as much as possible, hand it off to sort, and we're done. Now for built-in types, there's yet another trick. I didn't have to do this. I didn't even have to give it the comparator. it has a natural ordering. All integers are naturally ordered. All doubles are naturally ordered. All strings are naturally ordered. And you don't even need to create a comparator for them. Question?
So the compare to function, it can take integer strings or doubles.
Not this. It can only take what you parameterized it to take. So if you want a comparator for strings, say, what would it look like? Comparator for string, and then CMP string or whatever equals new comparator. Now, when I auto-generate this code, it will not take 2 integers. It will take 2 strings. And here I can do the same trick. O1.compare to O2. Or if I want it in descending order, I can go O2 compared to O1. Right? And then return, sorry. Yeah, go ahead.
So when you generate it, there's like an override. So does that mean originally there is a built-in comparator?
Good question. This gets into object-oriented programming that I don't want to do. But the interface does not have a default implementation here. It's okay to omit that. That was just auto-generated by the IDE. But if you put that, the reason that you would want to put that, this is called an annotation, and you've seen it before with respect to the testing suites that we've given you, is something called aspect-oriented programming, where you don't actually code functionality. Instead, you annotate it and say, this should have that functionality. And then the compiler or some other tool is responsible for coming in and auto-generating the code for you. Right? So override here is actually a non-functional annotation. It's just saying that this is being overridden from the superclass. Again, object-oriented programming, don't want to get into it too deeply. But leaving it off is okay, but if you put it in there, the reason that you'd want to do that is because if you don't actually override that, then that makes this into a red flag and says, wait a second, you said that this is overriding, but there's no compare function in the superclass there. This annotation is either wrong or this is wrong, you did something wrong. So the reason that you'd want to include that is for a sanity check, basically. Right? But for this class, leave it, add it. If it's auto-generated, why waste the 2 seconds to delete it? So how would this work in practice? Well, here, let's go ahead and go with a list of strings. Names equals array. This arrays.as list is just a quick way of creating a list without having to add, right? So Zoe, Adam, Alice, Bob. I'm going in order. I don't want to go in order. I want to show you that it will sort it for you. There we go. That's good enough. 4 names is good enough. All right. So now because strings are naturally ordered, you can go ahead and call collections.sort on names, and it will automatically sort it for you in lexicographic order in ascending order. So, oops. I want this. Print. There we go. Adam, Alice, Bob, Zoe. If you want a different order, like say descending order, then you do need to provide that comparator as an optional second argument here. Now when I run this, it'll be Zoe, Bob, Alice, Adam. Oops, oh, I do have to print it, sorry, to show you. Zoe, Bob, Alice, Adam. All right. Questions so far? No? Then how do we search? Right. There's a collections dot, what do you think? Binary search, right? And what arguments does it take? The thing that you're searching for, numbers, and the key that you are searching. So 42, say, right? So int result is equal to this. Again, no pointers here. I wonder what happens when you look for something that doesn't exist. In C, it was returning a pointer, so it returned null if it couldn't find 42. Let's find out what happens here. System.out, system.out.println result. This should be a successful search because 42 is indeed in there. 7. What is that? Let's read the documentation here. This method returns the index of the search key. So it's at index 7. Is that right? 0, 1, 2, 3, 4, 5, 6, 7. Looks right to me. What do you think it returns in the event of an unsuccessful search? 421. Let's find out. -10. It returns something negative, but here you can read into the magnitude of that. What is it, do you think? Let's read it. I don't know if you can see that or not, but I'll read it to you. The index of the search key, if it is contained in the list. Otherwise, it gives you this formula that you can use to determine if it were in there, where would it go? Right? And that's the index that it returns. So -10 here would be the insertion point. So -10, negative, that gives you +10. -1 gives you 9. That tells you that it should go at index 9 at the end. 421, it goes at the end. Right? So that's kind of cool, because if you wanted to say, search for something, oh, it doesn't exist. Well, okay, it belongs right here. Then I can go ahead and put it right there and add it at the same time. What about searching for names? Can I search for 421 in this array of names, or in this list of names? Doesn't make much sense, right? And consequently, it's not going to compile. You gave me a list of strings, but your key here is for integers. Didn't match, right? So add them. That will match. And it should return what? It should return the index at which it finds it. -1, it didn't find Adam. Why not? Because it's not ordered in the way that you expect it to be ordered. Descending order. This is going to assume ascending order. All right. So what can we do? Collections dot. Actually, no. We could resort it if we wanted to, or we could use a different version of binary search. You give it the thing that you want to search for, the key, and then the comparator that you want to use. In this case, descending. There we go. And this should be successful. Adam should be at the last index, which is 3. Right? There you go. 0, 1, 2, finally 3. What if you did something like this, where I'm going to search a list of names, a list of strings for the string Adam, but I'm going to go ahead and use a comparator for integers. Does that make any sense? Nope. So compiler error. You can't do that. Over here in C, you can do that all you want all day long. It's just that it's going to give you weird, unexpected, undefined results. Maybe, possibly, a segmentation fault. Right? So don't mix your types. Make sure that all of the assumptions are valid, etc., etc. Right? Questions? No? Then what does a comparator look like for non-built-in types? For example, I've got a student, right? Or not this one. Where's my student? Here we go. I've got a student structure, which is an NUID, a first name, a last name, a year, et cetera, et cetera, et cetera. What would a comparator for a student look like? This comparator orders student structures in ascending order with respect to ... How would you order a student? Alphabetically based on last name, and then if they have the same last name, Smith and Smith, Alice would come before Bob. All right. So name, what's an alternative? Name in descending order, right? GPA, ascending order, descending order. Right? Date of birth, oldest to youngest, youngest to oldest. Let's just do one of those, and let's do the first one that you suggested. All right, with respect to last name / first name. Okay. So int, copy, paste here, because it's always going to be the exact same signature. but I'm not comparing integers anymore. What am I comparing? Student. And I'm comparing them how? By name. Right? Give a descriptive label, right? All right. So typecast them. Actually, I don't want to copy all this. Typecast them to the appropriate type. They're not integers. They are student, student, pointers, student, 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 and student. Now I've got students X and Y. Right? I want to compare first on their last name. So how do I compare their last names? First of all, how do I get their last names? If X's last name comes before Y's last name. So in Java, we would have getters and setters, right? How do I get this last name here? X, arrow, last name. Why did you do an arrow? Because it's a student pointer. It would be wrong to do that because it's not a regular structure. So yes, good job. It is a arrow. Y's last name. Now, is that how I compare strings? Nope. How do I compare strings? Strcmp. It's going to return something negative, positive, or zero depending on the relative ordering of those strings. Sounds really, really familiar. Same basic contract here. But let's take a look at the man pages for strcmp. Is strcmp a comparator? What does it take to be a comparator? It takes the right stuff. Right? Const void star. Does that look like a const void star to you? Nope, it's not a proper comparator. Okay? So keep that in mind. You can't use it to sort an array of strings. If you want to know how to sort an array of strings, read the book. Right? Okay. If this is negative, then I will return something negative because their last name comes before the other guy's last name. Else if that same thing is positive, I return positive. There must be an easier way. If it's negative, return -1. If it's positive, return +1. If it's 0, return 0. Just return it and be done with it. Right. Now, there is a problem. What if they have the same last name? Does it matter if it's Bob Smith and then Alice Smith? We probably want Alice Smith, Bob Smith, right? So let's not return that right away. Let's go ahead and put that into a result. Now, if the result is 0, then that means that they have the same last name. Look now to the first. And at that point, I will return whatever the string comparator says for first name. First name. Making sure to return it, actually. There we go. Return. Let me check to make sure. Got nothing in chat, so no questions so far. All right. Else, return result. Now, why do I return result right here? Their last name is, I don't know, Anderson and Burke, right? And they're not the same, and so result would not be 0, and so you return that right away. Anderson comes before Burke. Yeah?
So were you saying that strcmp wouldn't work in this case?
It would not work to sort an array of strings, right? In this case, it works. The way that I'm using it is perfectly fine, right? Because it's all within another comparator. But if you want to create a comparator for strings because you want to order an array of strings, then that's a little bit more complicated. And we can do that on Thursday after the lab. Right? In fact, we will, because we also need to talk about how to, or go through some examples on how to actually sort an array of structures. Right? But there's your first comparator for student by name. Student by name descending, what would you do? Same trick. Call the other one reverse. Student by GPA. Same basic kind of pattern, but instead of looking at the last name, first name, you'd look at the GPA. Don't do the difference trick. 3.75 minus 3.25 are not the same thing, right? Questions? No? How would you do this in Java for your students? I'll go ahead and get rid of this. Oops. How can I create a comparator for students? Comparator for student. CMP student by name, right, is equal to new comparator. Oops. There we go. I spelled it right. All right, you fill in the blanks for me because I don't want to type that all out. I'll go ahead and go and rename them A and B. How do you want to compare your students? Same way, last name, first name. All right, so same exact pattern as before. Here we go. Result would be A dot, okay, fine. Okay, I don't know what the hell that was, but A dot get last name dot compare to B dot get last name. Right? There's your result. If your result is 0, then go ahead and look at the first name and do what? Return first and first. Otherwise, return result. Oh, sorry, what? First, fist. There we go. First and fist. All right. Now are you okay with that? Incorrect number of arguments. Wait, what? All right. Start over and see what you're complaining about. Oh, you know, did I delete something else? What? Add unimplemented methods. Okay. Now you're compiling. All right, fine. And cut, paste, get rid of this, get rid of, and then A and B. I think I had a superfluous curly bracket in there somewhere. There, clean it up. All right. And I don't have any student objects to play around with, but we can do that next time. Now, next time also, I'll show you some additional tricks that were introduced in Java 8 or 9 or something like that, where it's completely new syntax here. So comparator, off the top of my head, C equals comparator dot build, comparing, there we go, student first name. I think that this is it, get first name maybe. There we go. I did it off the top of my head. Awesome. Right. So let me walk you through this. This is the exact same comparator here, almost. Let's go with last name first, though. There we go. So comparator, instead of building this comparator from scratch, what you can do is you can use this comparing, and then this is brand new syntax. Has anybody ever seen the colon before? Where, in what?
I've seen it like somewhere, I think it's one of the files.
Oh, okay, so in one of the files we gave you? All right. Has anybody seen it in any other languages or anything like that? C# might have it? I'm not sure. Probably it does. I'm not sure about Python, but it's the method selection operator. I think it originally comes from C++, where basically you're building a comparator. How do you want to compare? I want to compare using the student's get last name method. Right? It's kind of like a function pointer. You know, it's not actually calling the function. It is, I want to use that function over there, that method over there. Well, where does that method belong? Where does that method exist? It exists in the student class. : says class : method, and then you can string these things together. That then comparing student get first name. And then if you want to get then comparing, what do you complain? Oh, there. No, I'm getting to. There we go. Comparing student, then comparing that dot reversed. There we go. You can reverse it all. Then you can. What I want is then comparing student get age. There. Now if you have two John Smith, the older one will be first, and then the younger one will be second. Right. Cool? That's I didn't even have to take until next time to show you this cool syntax. If you want to use this syntax, great. Usually what you do is like this, though. You go dot on this next line, then dot, then dot. Right? You could put it all in one line if you really want to. In fact, I think that if I auto formatted this, it would probably would do that. Yeah. This is much better, though, right? Why? Because now you can read it. Comparing, then comparing, and you see all these things all together in one one convenient place. Yeah.
Is that only if you're comparing like non-standard type?
Right. If you're comparing standard types, don't even bother with a comparator, right? Just use the natural ordering like this. Right? And then I guess if you wanted to, you could also go once you've got this names dot reverse. Nope. List dot reverse. Nope. Collection dot reverse. There we go. Names. Right, there. So if you want a descending order, don't bother making a comparator at all. Sort in ascending order, the natural order, and then simply reverse it. So no need to write anything really fancy in Java. Right. Okay, we'll pick it up there. Oh yeah, go ahead. Strings are a built-in type, and so they are naturally ordered. Right. They're, as we've already seen, strings are, in fact, a lot of things are way better in Java. Or I don't want to say way better because that's a value judgment. They're a lot easier to use in Java. That ease comes at a cost. Java is not winning any performance tests against C at any time. No language will ever match C. Well, I don't want to say never, but the performance-wise, you're never going to get the performance that you get with C with Java. Yeah.
So is, like, Java uses much more space?
Java is a lot more overhead because, first of all, Java virtual machine, no memory management, so it's adding on top of your program all this monitoring to say, okay, well, that thing is eligible for garbage collection, that thing is not. Even this stuff comes at a cost. This was all added in later Java, so it's all just syntactic sugar. What's going on under the hood is the Java compiler is going in and saying, okay, I'm translating that to some old school Java, right? And if you actually were to decompile, you can decompile Java code. And if you were to decompile this, it would look nothing like what we have here. In fact, if you looked on the binary folder, even in your own IDE, you'd see all these brand new mysterious classes, right? You'd have a mysterious class with some weird name and then a $sign and then class 001, because the way that it does anonymous inline classes here is it takes your code, copies, pastes it, and actually creates a class that it can actually deal with. Again, it's just syntactic sugar. It is the compiler doing a lot of the work for you. All right, we'll start next time.
We don't have a lecture next Tuesday.
Next Tuesday, no.